Hello, welcome back to the Meta Mathematics Club review videos. So this time I'm going to be talking about what I did last week. Sorry that this video is incredibly late. I had a very hectic weekend. But yeah, let's go into the math. So here's a recap of what we did last time. If you're a little confused, you can just go back and watch the video again. So we talked about the problems of using English to describe mathematics. It's a very confusing system for this kind of process, and here are some of the problems it makes. So 1 is the smallest number bigger than 0, has no truth value, or at least no meaningful truth value. It could be true in the natural numbers, it could be false in the rational numbers. So it has no inherent truth to it. It depends on what you're working in, so to speak. And this sentence is false. You probably all heard that. That's a non-mathematical statement. You can't assign a truth value to it. So at the end, you tried to make your own mathematical grammar, hopefully, and that is something which determines which strings are mathematical statements. So, for example, it's just like a little bot that says, yes, this is a mathematical statement, or no, this is not. And that's what a grammar is. It'll tell you what string, what list of characters is a mathematical statement, and what is complete garbage or anything that isn't a mathematical statement, like the word blueberries. So let's talk about what Gottlob Frege, or whatever his name is, did. So this is him. He decided to make the standard math grammar we use today. So it tells you what is a valid mathematical statement and what isn't. So during his lifetime, he remained completely unrecognized, but although his work is widely used today, he remains an obscure figure. So nobody really knows who he is. Couldn't get much information on him, how he made this, when he made it. I just found out that he made it. So we need to understand what a monosorted vocabulary is. And whoa, I'm bringing out all the cool kids terms first. Yeah, this is going to get complicated, this video, so feel free to pause and go back at any point. So a vocabulary consists of a bunch of symbols, each with an assigned type. So it's just a set of symbols, and that really has no meaning. Symbols are just distinct. They carry no inherent information other than being different from each other. And each of them have an assigned type to them. There are 3 types: constant symbols, function symbols, and each of them you give them an arity, a number. It doesn't actually matter what this number is. Arity doesn't need to be defined yet. You just give them a number and call that number their arity. So we're not going to talk about what arity means yet. And relation symbols, you also give those an arity. So I'm going to go to the whiteboard now and explain a little bit about what these are, make some vocabularies, work a little bit. It'll be cool. All right, so we're here at this whiteboard. Well, as you can see, it's not actually a whiteboard because it's only a board. It's not actually white. So instead, we're going to be calling it from now on the spicy board. Excuse my handwriting. And yeah, this is only Spicy Board iOS number 5, so I'm unable to use Comic Sans or color. I know you all love that Comic Sans with its beautiful kerning, but, well, we should probably talk about vocabularies then. So, you can probably guess what the meaning of a constant symbol is. It's just some sort of representation of some sort of constant. So 0. You can make a symbol for 0. It wouldn't be 0, but it would be a symbol for 0. It sort of represents 0. 1. Once again, represents 1. Pi represents pi. Doesn't actually mean pi, just represents pi. You can also write these quotes like these. Those are called Quinean quotes, and they're ugly and evil, so we're not going to use them. So you've got function symbols. They act sort of similarly. So we've got f. What does f mean? Who cares? It's a function symbol now. Zeta. That represents a Raman zeta function. That's important. Gamma. Loads of things are called the gamma function. Does it matter? No. Gamma is just a symbol, not a function. These are all symbols. They aren't actually anything meaningful yet. You have to give meaning to them. And last but not least, we're going to use operators. Operators are also functions, so we could give symbols for them. And finally, probably the one you were most confused about, relation symbols. What the heck are these boys? Well, let me tell you. These are less than. That's an example. Equal to. That's an example. Approximately equal to. Greater than or equal to. Similar to, or if you're talking about anything other than geometry, which I am only going to talk about anything other than geometry, isomorphic to. Loads of other examples. But these are all something called binary relations, which means that there's one thing on the left, one thing on the right. Two things total. Doesn't accept more. You can also have things like, is a great boy of X, Y, Z. That's a truth statement on X, Y, Z, asking if X, Y, and Z are all great boys. And if they're not all great boys, then it's false. So then we can make a relation symbol for this. Is a great boy. Now that's a relation symbol. So that's what these symbols are. You've got constant symbols in each vocabulary, function symbols in each vocabulary, and relation symbols in each vocabulary. All right, so we just came back from our excursion to the lands of spice, specifically the spice board. And we learned that there are 3 types, constant symbols, function symbols, and relation symbols. I still haven't explained arity. Just keep in mind that that's just an arbitrary number that you associate with each, and it doesn't actually matter yet what that means. We're going to come across what that means later. So there are 3 types: constant symbols, function symbols, relation symbols, and dairy-free. Now let's go on to the next slide. So the letters usually used for a vocabulary are tau or sigma, in the same way that a natural number is usually represented by n or k or m, something like that. Real numbers are usually represented by x, y, z, w, same thing. And they're just sort of variables, placeholders for the vocabulary. Sometimes, by set theorists like me, vocabularies are wrongfully called languages, and this is a miscarriage of justice. And for reference, here is a miscarriage, pictured right. So now that you have a vocabulary down, let's talk about terms. Now, I'm not sure you have a vocabulary down. That's okay. This is a really confusing lesson that's not going to make much sense. But you can go back in the video and try to understand what that means. So terms are sort of the smallest meaningful strings of first-order logic. So they try to build other objects out of constant and function symbols, and they also introduce a new type of symbol called the variable symbol. So you can sort of build objects in the same sense that you can build new numbers out of 0, 1, and plus. You can do 0 plus 1, that makes 1. 0 plus 1 plus 1, that makes 2. You can build all those new objects, and those are the objects we're going to try to create using constant, function, and variable symbols. So if tau is a vocabulary, you see what I did there? That's like saying if n is a natural number, or if p is a prime, then the tau terms are defined as follows. The terms that you can make out of tau. If x is a variable or constant symbol of tau, then the string just x is a tau term. And if f is a function symbol of tau with arity n, so that's where it becomes important. So t, s, and v are other tau terms. The string f of t, s, v, ... etc., etc. So you have these n many tau terms, right? These are things like 0 plus 1, depending on what tau is. If tau has 0, 1, and plus. 0 plus 1, 1 plus 0, 1 plus 1. You can combine those all together with this little function symbol f. So basically, you can just put all of those tau terms in the middle of a function. So that definition is already confusing as hell. So this is going to be the vocabulary where we're going to be using it. And now to the spice board we go. And we're back here at the spicy board, and now we're ready to talk about terms. So, you've got a vocabulary, tau. Oop, that's very out of focus. Please focus. So you've got a vocabulary, tau, and the tau we're talking about has the constant symbols. Oop. Let me just write that down. 0 and 1. And it has the function symbols of just S, and it has arity 2. Remember, now this is just, arity 2. And for now, this is just an arbitrary number we're giving S. So this symbol just has arity 2. It doesn't really matter why. There's no explanation for why it has arity 2. We just sort of gave it arity 2. And it also has the relation symbol of less than. And we're going to make V a variable symbol, but it's not part of tau. Variable symbols are not in any vocabulary. Tau is a vocabulary, doesn't have any variable symbols. Variable symbols are just sort of their separate own thing. Anyways, so we're going to try to make some tau terms. So here's an example. So you've got 0, that's a tau term. 1, that's a tau term. We just use these constant symbols right here. So those are both tau terms. And, well, V is also a tau term since it's a variable symbol. But now look at what we've got. For any of these tau terms, we can just put them in a function together. So we've got S of 0 and 1, and, well, hold on. How many of these things can I fit inside S? Well, to make it a valid tau term, I need to have some sort of maximum limit. You know, for example, the zeta function only accepts 1 input. But other things accept 2 or 3 inputs, like 0 plus 1, which you're going to write like this for some stupid reason. So what's the meaning of this? Well, we're just going to give S, maybe, some sort of number which represents the maximum objects it can hold, the maximum number of objects it can hold. And it can actually only hold this number of objects. It can't be anything smaller or bigger. So S has arity 2. We'll put 2 things in it. So you can't put S of 0. That's not a valid thing. S has arity 2. 2 is bigger than just this thing. S of V1, that's a valid thing. But S of V1, 0, uh-oh, that's more than 2. So you can only have the arity of things inside of the function symbol. So that's what arity means in terms of function symbols. So these are all tau terms, but relation symbols aren't in tau terms. You can't combine a relation symbol to make a new object. You can't combine a relation symbol with other things to make a new object. For example, if you take 0 plus 1, you can't combine it with less than and 2 plus 0 to make a new object. That just becomes a truth value. So we're going to not use them. So for example, hold on, let me just mark which ones are not. S of V1 is less than 1. That's invalid. It has this thing. So that's not right. But just S of V0, that's fine. So now you've seen all these examples. This one's correct, this one's correct, this one's not, this one's correct, this one's not. You've seen all these examples of making tau terms. So go off and make your own of these weird, fancy, pantsy, schmancy tau terms. Now, Okay, so we're back on the regular space, and hopefully you've made some of these tau terms. And now I'm flipping it over. I'm going to ask you which of these boys are tau terms and which of these are not. So here's for reference the list. So go ahead and discuss with yourself. Okay, hopefully now you're back. The answer was this one is a tau term, this one is a tau term, this one is a tau term, this one is not, and this one is not. So it's everything except these last two. Those are both wrong. So now we have terms, and terms are pretty expressive, but we still have some problems. So stating things like x equals 5 and x is less than y are both impossible. You can't do either of those things. What if we want to do those things? We're trying to make valid mathematical statements. It's safe to say that these are. So we got to add more to first order logic to make it a sort of complete statements. So let's make something which fixes that issue. So we're going to make our atomic formulae. So like using n and k and m for natural numbers, we're going to use phi, psi, and chi, the Greek letters, for atomic formulae. So an atomic formula phi of tau, where tau is some vocabulary, is one of the following. So it's a string of the form r of t sv is true for any tau terms, t, sv, etc., etc. So if you have a bunch of tau terms, you can compare them with this relation. If you remember relation symbols, just ask whether or not something is true about a bunch of objects. So these tau terms are objects, and we're asking if this r is true about them. And you also actually just give it equals. You're allowed to use equals regardless of whether or not it's in the vocabulary. We treat it as its own separate thing. So you can say A equals B. So make an atomic formula for tau, where tau is the vocabulary described before with 0, 1, s, and less than. So I'm going to go let you do that. Write it down now. There you go. And all right, so hopefully now you're back from that. I'll go make some of my own on the spicy board. So we're back here at the spice board, and just for reference, I have the required tau listed out. We've got the constant symbols, the function symbols, and the relation symbols. So we're going to make some atomic formulae. Focus. Phi. So here's what phi has. It can be r of t, v, s, where t, v, and s are tau terms, so basically objects made of function, constant, and variable symbols. And it's got t equals v, or v equals s, etc. Those kinds of things for other tau terms, t and v and s. So let's make one. So we can start by making some tau terms. So we've got those down. Let's say s of 0 and v. So remember, we can use this variable symbol v here. So this is a nice tau term. So let's make something out of that. Let's also make this tau term 1. That's a nice tau term. So those are both tau terms, but they're not yet atomic formulae. So phi is going to be, let's use this less than symbol as our relation symbol, and we're going to use it kind of awkwardly. We're going to say less than is true about s of 0 and v, and 1. So that looks really weird. But basically it's just the same as saying s of 0 and v is less than 1. It's just another way of notating it that's more common with the way of notating functions. So we're going to write it kind of like that. So we've got s of 0 and v is less than 1. This is a valid atomic formula, since we've got tau terms in the middle, and we've got this relation symbol on the outside. But wait, once again we've run into this problem where we don't know how much stuff we can put in here. For example, if I just put in less than of s of 0, v, and then I just put in 1, 0, 1, what is this supposed to mean? This obviously means this. We can interpret it quite easily, but this doesn't have any easy to understand meaning. So what we're going to do is we're just going to ban this, say, no, you can't do that. You can't come into my country and start asking questions about whether or not I'm still Christian and then burn me. You can't do that at all. So we're going to ban that. Instead, we're going to say you can only have 2 things in here. That sounds kind of familiar. You can only have 2 things in this S thing also. Maybe we should give them the same name, like arity. Wow, this has arity too, or it's binary. So that's what the arity means in terms of these less than things. So we've got that this is a valid one, and we've got, we can also do equals, so s of 0, v equals 1. That's fine. Whether or not it's true, it's valid. It's grammatically correct. S of 1, 1 equals v. That's valid. You can do all these sort of things. So now I want you to go and try and make some of your own. Alright, so we're almost done. We've got all of the atomic ones. So we're going to do... Oops, why do I still have quantifier free up there? Imagine I don't have that. So let's describe all of the first order formulae together, and then we'll be done. That's all of the valid grammatical sentences of first order logic. So, oh, that's why. A quantifier-free first order formula, phi, of the vocabulary tau, is one of the following. So we've got atomic formulae, the string not phi, so this is, or not psi, this is interpreted as psi is false for any other one. So you can basically do psi is false whenever you have another first order formula. You can't do this sentence is false, but you can do the following sentence is false. 1 is greater than 0. The string chi and psi, and I know that looks really awkward, but that's what that means. That means and. Chi and psi for any other first order formulae, chi and psi. So these are both true. So you can say the following is false, or you can say this is true and this is true. And you can say any of the atomic formulae already described. So x equals y, x is less than y, stuff like that. So we only used and not in that. But what about stuff like or and this implies this? Well, A implies B, A or B is true. These can all be derived from and not. And to see why, you can look up logic gates. It's a fascinating study. Basically, you can just construct all wanted logic gates out of and not, and that's it. And if you were in the class, then Benjamin could probably explain this because he knows all about logic gates. And at this point, I actually suspect Benjamin is just a bunch of logic gates. So he'd probably know a lot about it. So now we're almost done. We're going to define all first order formulae. So we just need to tackle this. Let V be a variable symbol that's used in the formula psi. So, yeah. V is something that's used in the formula psi. So for example, V is less than 5. V is that symbol that's used in psi. So if psi is quantifier free, then V is called free in psi. In other words, it still acts like a variable. This just means that you can still fill in the blank. So in the example x equals y or x is less than y, you can put something in x and something in y, and it would be grammatically correct. So you could put 0 in there, it would be correct. You could put 1 in there, it would be correct. You can still put whatever you want in there. So now we can define first order formulae, finally, now that we have the notion of free variables. So a first order formula, phi, of the vocabulary tau, is any of the following. So you've got the quantifier free, so you've got and, not, and other logic gates, and you've also got the atomic ones, so that's a lot. And you've got for all v, psi is true, where psi is any other first order formula where v is free. So, for example, if psi is v is greater than 0, you've got for all v, v is greater than 0. And there exists some v such that psi, where psi is any other first order formula such that blah blah blah, that's the same thing. There exists some v such that v is greater than 0. In these examples, v is no longer closed in here. You can't say for all 1, psi is true on 1. You can't say that. You can't say there exists 1 such that psi is true. So v is actually closed. It's not free anymore. Yeah, that's a problem. You can't use v anymore. You got to use a different variable symbol. But now we're done. If we have time left, go work out some examples on the whiteboard. And right now, it's sort of like 11:30 when I'm making this video, so I'm actually not going to do that. Really sorry about that. But feel free to go back and watch any part of the video. And bye. Thanks for watching.